Hello dear students, in the last class we talked about dimensions, dimensional formula, dimensional equation. Now we are going to see the applications of the concept of dimensions, dimension formula or dimensional equations here. So let us try to solve the problem based on dimensional equation. So dear students, let us solve a problem which asks us to convert from one system of unit to the other system of unit. We know that we can use method of dimensions to convert a physical quantity from one system to the other system. Now what our problem says is, a calorie is a unit of heat or energy and it equals about 4.2 joule. So 1 calorie is equal to 4.2 joule, where 1 joule is equal to 1 kilogram meter square per second square. In that case, it says that suppose we employ or we use a new system of units in which the unit of mass equals alpha kilogram. So alpha kilogram, this is the new system of unit, the length equals beta meter and the time gamma second. And we are being asked to show that a calorie has a magnitude of 4.2 alpha power minus 1, beta power minus 2, gamma power 2 in terms of new system of unit. Now to solve it, we know it says that 1 calorie is equal to 4.2 joules. So let us put this way, 1 calorie is equal to 4.2 joule. When it is said joule, so 1 joule is equal to 1 kilogram meter square per second square. So I write this one as 1 kilogram meter square per second square. So for me this is the old unit. I want to convert this measure into a new system of unit, where the new system of unit gives me that alpha kilogram, this is the new system which is equal to 1 kilogram in the old system of unit. This is new system, this is old system. Likewise, here it says that for length beta meter is equal to 1 meter. So this is the new system of unit, this is the old system of unit, and for time it says gamma second is equal to 1 second. In the sense, this is old system of unit and this is new system of unit. Now we have already studied that the measure of or the magnitude of a measure in new system of unit, magnitude is equal to the magnitude in the old system of unit times see m1 by m2 power. So I have here for mass it is 1, the dimension is 1, m L1 over L2, the dimension is 2, and T1 over T2, the dimension is minus 2. The dimension is minus 2. So in our case, this M1 new system of unit is 1 kilogram, in the sense old system is 1 kilogram and the new system is alpha kilogram. So I am going to write N2 is equal to N1. N1 is 4.2. So as such 4.2 times the old unit is 1 kilogram over the new unit, equivalent unit in the new system is alpha kilogram. The dimension is 1, and L1 the old system of unit which has meter over in the new system of unit it is beta meter. So I write beta meter and the dimension is 2. As such the new system for T1 it's second over gamma second. So this gamma second and the dimension is minus 2. Now here this kilogram goes off, meter and second, as such I am left with N2 is equal to 4.2. Alpha is in the denominator and the power is 1, so I can write alpha power minus 1. Beta is in the denominator, so I can write beta power minus 2. Gamma is in the denominator and inverse minus 2, so this is going to give me. So therefore, this is the required result. So this is the solution which we have been asked to show and we have shown. So this is the one aspect of the application of the method of dimensions. The second application of method of dimensions is to check the correctness of a physical relation. What is a physical relation? In physics, a physical event is described using all the physical quantities involved in it by relating those physical quantities in the form of an equation, and that is what we are calling it physical relation. So let us try to see an example using which we will understand how to check the correctness of a physical equation or physical relation. It says that a book with many printing errors contains 4 different formulae. So these are the 4 different formulae for the displacement of a particle undergoing a certain periodic motion. So a particle is undergoing periodic motion and that motion is being described with the help of a physical relation. These 4 are the physical relations. Now, we are asked to rule out the wrong formulae on dimensional grounds. So therefore, we need to check whether these formula are dimensionally correct or not. Whichever the formula is wrong based on the method of dimensions, we are going to rule out that formula. So we have to identify. So here the first one is given, y is equal to a sine 2 pi t over t. Likewise 4 different formula. However, some description is given here. It says that a is the maximum displacement of the particle. So a, whatever the symbol here we have a, all represent displacement, and v is the speed of the particle and t is the time period of oscillation. Now see please, a physical relation is correct only if the method of dimension of, or in the sense I would say dimension of a physical quantity on the left of the equal sign must always be equal to the dimensional formula of all the physical quantities involved on the right hand side. Let us try to check the first one whether it is correct or not. Now the first physical relation, if I look at, I have y is equal to a sine 2 pi t over t. Now the dimension of the physical quantity that I have on the left side, so this represents the displacement. So this will have only displacement, so m power 0 L power 1 t power 0. So this is the dimensional formula for y. As such, if we see on the right hand side, we have a. For a, it is said that a is amplitude or displacement. So for displacement, it is again m power 0 L power 1 t power 0, and when we take for sine 2 pi t over t, now if I see here 2 pi, this is angle and this will not have any dimension. Time in the numerator, time in the denominator. So again the dimensions will cancel out, or sine 2 pi by t is a dimensionless constant. As such, I have m power 0 L power 0 or t power 0, or I should say that 0 dimension in mass, 0 dimension in length and 0 dimension in time. So on the right hand side, I have the product of a sine 2 pi by t. So I am going to find the product of these 2 dimensions. So when I find here, I would have a sine 2 pi t over t, and if I talk about the dimension, I am going to have m power 0 L power 1 and t power 0. Now if I see the right hand side and the left hand side, I see the dimension here and the dimension here, both are same. So therefore I would say that dimensionally this is correct. Similarly, we can check the second one too. When we try to see the second equation, I have y is equal to, I want to check whether it is equal or not, dimension of a sine v t. I want to check this one. To check here for y, again this is the displacement, so this will be like this. On the right hand side, if I see a, already it was told that it is displacement, so this will have one dimension in length. And when I look for this sine v of t, for v I have m power 0 L power 1 t power minus 1, because this is speed and this is time. When I put time, so t power 1, so this is 0, however we have L power 1. So sine, see please, on the face you have a dimension of 1. So therefore this dimension on left hand side is not equal to right hand side, therefore this is dimensionally incorrect. Had it been that this face was a dimensionless quantity, then this relation would have been correct. But since this face has a dimension of L power 1, therefore this relation is dimensionally incorrect. So we can rule out B. Let's check C. On the same line, if we have y is equal to a over capital T sine t over a. When I check the dimension here, it is m power 0 L power 1 t power 0. And when I check on the right hand side, I am having, this is displacement at the numerator, and at the denominator it is time period, so m power 0, L power 0 and t power 1. And when I talk about the dimension of this at the numerator I have m power 0, L power 0, t power 1, and at the denominator this is displacement, and this works out to be m power 0, L power 1, t power 0. And if I check here, I have L power 1, t power minus 1, and here it is t power minus 1, L power minus 1. So this works out to be m power 0, L power 0, t power 0, where the two dimensions are not equal. So we can rule out the expression C also. So this is dimensionally incorrect. Let us check the fourth one. Fourth equation. When I check the fourth equation, I am given y is equal to a over root 2 sine, it is given 2 pi t over capital T plus cos 2 pi t over capital T. Now here for y the dimension is m power 0, L power 1, t power 0, since it is a displacement. At the denominator I have root 2, so it is a dimensionless constant, no dimension. For this a is amplitude, so I have m power 0, L power 1, t power 0. Sine of this is the total phase, and if I check, see 2 pi t by t, so 2 pi has no dimension. This has a dimension of time, this has a dimension of time, both cancels out. So this quantity has no dimension, and let me remove this bracket. The bracket must be here, and the bracket here, it is here. So in that case, this is a dimensionless quantity, and here when we look at, this is also dimensionless. So therefore the trigonometric ratios that I have within the bracket has no dimension. So therefore these two dimensions are equal. I would say that the D part is correct, so dimensionally correct. So these two are ruled out, and these two are dimensionally correct and are acceptable. So the next question is, it says that check the dimensions whether the equation given is tan theta is equal to rg over v square or square of the speed of the particle is correct. So, we have to check whether it is correct or not, where r is radius of the path, g is acceleration due to gravity, v is equal to speed of the vehicle and theta is the banking angle. As you move into the chapters, you will find that this is an expression given for an object that negotiates a turn on a banked road. The correct formula for this physical relation is actually tan theta is equal to v square by rg. If you take note, you will understand that v square is at the numerator and rg is at the denominator, whereas the formula is given as, or relation is given as, tan theta is equal to rg by v square. So, the correct one is this, however given one is this. We are asked whether this expression is dimensionally correct or not. This is the physically correct expression. This relation is physically correct relation. The given relation tan theta is equal to rg over v square is physically incorrect relation. This is physically incorrect relation. As we study the topic, we will come to know that we will derive this relation. However, we are asked to check whether it is dimensionally correct or not. So, to check dimensionally correct or not, let me rewrite the relation first. Tan theta is equal to rg over v square. Tan theta, trigonometry ratio, which is a dimensionless constant. So, therefore, left hand side has no dimension. So, m power 0, l power 0 and t power 0, which is equal to, when I look at here, when I try to write the dimensions of the respective physical quantities, I am going to have r is the radius of the path. So, radius, so it will have one dimension in length. G is acceleration due to gravity, for which we have already studied, acceleration due to gravity, one dimension in length over 2 dimensions in time. So, acceleration over speed, square of the speed. So, as such, square of the speed, so 2 dimensions in length and minus 2 dimension in time. So, if I check here, see this dimension and this dimension goes off and this dimension and this dimension goes off. Otherwise, I am left with m power 0, l power 0 and t power 0. Otherwise, the right hand side also has 0 dimension in mass, 0 dimension in length and 0 dimension in time. So, which is equal. So, I would say that this relation or this equation, given equation is dimensionally correct. So, given equation is dimensionally correct. So, the given equation is dimensionally correct, but as I said at the very outset of the problem that the given equation is tan theta is equal to rg by v square. The correct relation for this one is this physically correct relation. V square must appear at the numerator. So, one thing, dear students, must keep in mind that the physical relations which are dimensionally correct need not be physically correct one. This is the point that must be highlighted with the help of this equation or this problem. So, the next application of method of dimension is we can use method of dimension to derive a relation among the different physical quantities that are involved in any physical event. Let us try to understand how to use method of dimensions to derive relation using one problem. The problem given is, it says that the velocity of water waves depend upon their wavelength lambda, density of water rho and the acceleration due to gravity g. We have to find the relation among these physical quantities using method of dimensions. So, the very first step that what we are going to do is, we have learned through this problem that the velocity depends upon the wavelength, it depends upon the density of water, and it depends upon the acceleration due to gravity. So, as such, I am going to write the velocity depends upon wavelength, it depends upon density, it depends upon acceleration due to gravity. But how it depends, I do not know. So, therefore, I write lambda power a, rho power b, and g power c. However, this is velocity. I know the dimension of the velocity. As such, I am going to write m power 0, l power 1, t power minus 1. This is proportional to, this is wavelength. So, as such, I am going to write wavelength, the dimension is L power A. So, this is the dimension. Next, density, mass by volume. So, I have mass power B, volume is L power minus 3B. And acceleration due to gravity. So, I will have L power 1 t power minus 2. So, if it is L power 1 power c, so this will be L power c and t power minus 2c. So, once again wavelength, so L power A, mass by volume m L power minus 3 power b, so m power b L power minus 3b. Acceleration due to gravity is L t power minus 2 and whole power c, so L power c t power minus 2c. Now, if I try to assemble all L at one place, so I am going to get L. So, first let me write m, so I have m power b, and when I go for L, so I am having L A minus 3b plus c, A minus 3b plus c and t power minus 2c. So, this is m power 0, L power 1, t power minus 1. Now, I am going to equate the dimension of mass from left hand side to right hand side, and I have b is equal to 0. Second, if I look at, I am going to equate the dimension of L on left hand side with the dimension of L on the right hand side. So, I have A minus 3b plus c is equal to 1. Thirdly, the dimension of time on the left hand side I will be equating with the dimension of the right hand side time. So, I will have minus 1 is equal to minus 2c. So, I have got the value of b. From this I am going to have the value as c is equal to 1 by 2, and I have to get the value of a. So, I can substitute the value of c and b over here. So, b is 0, so this works out 0 plus c is 1 by 2 is equal to 1, otherwise a happens to be 1 minus 1 by 2 is equal to 1 by 2. Now, I can substitute these powers over here. So, thus I have v is proportional to lambda power a is 1 by 2, rho power b is 0. So, this speed is independent of density, and g it is 1 by 2, c is 1 by 2. As such, if I rewrite this expression, I am going to get under root of lambda into g. So, this is the relation between the physical quantities that is or that are given in my problem. We can notice one thing, that I have derived the relation, but I failed to find out what is the proportionality constant. So, this is the drawback in the method of dimensions. Using method of dimensions, we can derive relations among the physical quantities, but we will never be able to find out what the proportionality constant will be. The next application of method of dimensions is, we will use the method of dimensions to find the dimension of constant in a physical relation based on the principle of homogeneity. Let us try to understand through an example problem. So, it says that find the dimension of A times B. So, we have to find the dimension of A and B, and then we have to find the product of the dimensions. So, find the dimensions of A times B in the relation given is this: P is equal to B minus x square over AT, where P is the power, x is distance and t is time, it is given, right. So, I need to find the dimensions of A times B. So, how is it possible? Now, when I see the given relation, I have P is equal to B minus x square over A times t. When I see the numerator, see please, the physical quantity x is distance, so square of distance. Now, when I see B, so see B minus x square, so this is square of distance, so definitely B must be square of distance. See, two physical quantities, when one physical quantity is subtracted from the other one, so the nature of the two physical quantities must be same. What I mean is, dimension of the two must be same. As such, the dimension of B must be same as that of the dimension of x square. So, I would say that dimension of B is equal to dimension of x square. It is said that x is distance, so therefore, the dimension is L power 2 or 2 dimensions in length. So, I have got the dimension of B. However, I want the dimension of A. Once if I find, then I can find the product. Now, to find the dimension of A, I see that now the numerator B minus x square, dimension of B and dimension of x square both are same. So, at the numerator actually the dimension is 2 dimensions in length. At the same time, by B minus x square by, so the dimension of A and t. So, if I find the dimension of, I would say that dimension of x square over dimension of A t, this must be equal to the dimension of power. This must be equal to the dimension of power, because here at the numerator these two dimensions are same. I am talking about dimension. So, dimension of say either B minus x square or simply say x square, both are same. In that case, I would say dimension of x square over dimension of power is dimension of A times t. Otherwise, I would say dimension of this dimension of power, dimension of t will give me the dimension of A. So, as such, if I further move ahead, I would say that dimension of A for me is equal to, at the numerator it is dimension of x square, so it is 2 in length because x is distance, P is power. So, over, we know the dimension of power, it will be work by time. So, force into distance. So, it is m power 1, L power 2, T power minus 2 times T power minus 1. Okay. Work by time is power, and the dimension of T is once again time. So, this is T. If I work out, then this will be equal to this and this gone, and this and this gone. So, I am having m power minus 1 t power 2. So, this is the dimension of A. Now, I am asked to find dimension of A times B. So, dimension of A times B if I am asked, then for me this is L power 2 times m power minus 1 t power 2, or else I will have minus 1 dimension in mass, 2 dimension in length and 2 dimension in time. So, this is the dimension of the product of the constants A and B. So, dear students, during this session we have solved many problems studying the applications of the method of dimensions. In the next class to come, we will talk about the errors involved in the measurement. Till then, study well. Goodbye.